WPR. Number 6. Remember, when working with absolute value inequalities, we need to get the absolute value isolated. So in this example, I'm going to subtract 6 from both sides. Then I can remove the absolute value to get 3x plus 4 is less than 2, and also 3x plus 4 is greater than negative 2. Subtracting 4 from each side, I would have 3x is less than negative 2, or x is less than negative 2/3. Also subtracting 4 in the other inequality, 3x is greater than negative 6, or x is greater than negative 2. Now, remember, the farther away you are from 0, the smaller the number is. So I would say that negative 2 is smaller than negative 2/3. So can you find a number that's bigger than negative 2/3 and smaller than, can you find a number that's bigger than negative 2 and smaller than negative 2/3? Yeah, like negative 1. So the fact that we can find a number that satisfies both of these inequalities means that this is an and in between. So I could say that negative 2 is less than x is less than negative 2/3. On a number line, I would have my negative 2 and my negative 2/3. Open circle, because there isn't an equal to symbol, and shade in between. It's a barbell. Remember, when working with negative exponents, you should take the term that's being raised to the negative power and move it. If it's in the numerator, it would move to the denominator and the exponent would become positive. And if the term with the negative exponent is in the denominator, it would move to the numerator and the exponent would become positive. So in this example, on the inside, I have a w to the negative 5, which is going to go into the denominator as w to the power of positive 5, and the w to the negative 9 will go into the numerator as w to the power of positive 9. Because these are powers with like bases, I keep the base and subtract the exponents. When you're dividing powers with like bases, you subtract the exponents. And I can now take this power of 1/4, and make it the square root. Raising something to the power of 1/2 means to take its square root. The square root of w to the 4th is w squared. In example 3, we have a higher degree polynomial, so we can't use the quadratic equation or completing the square. We have 3 techniques available. We can factor out a GCF, but this term does not have an x, so I cannot factor out a GCF. A second strategy to try is a difference of 2 squares. We have 4 terms. This is definitely not a difference of 2 squares. Lastly, I factor by grouping. That is, I can factor a GCF out of these first 2 terms. That would be x squared. And I factor a GCF out of the second 2 terms. That would be 16. And now I have 2 terms, 1, 2, that both have a common factor of x minus 3. So I factor that out, and when I factor the x minus 3 out of this, I'm left with x squared. And I'm going to write that x squared a little closer here to where it belongs. And when I factor the x minus 3 out of this, I'm left with 16. And I can set both of these equal to 0. So I add 3 to both sides to get one of my answers here. I can subtract the 16 over and take the square root, and I would get plus or minus 4i, because the square root of negative 1 is I and the square root of 16 is 4. So my answers would be plus or minus 4i and 3. In this example, we have a quadratic. It's not a higher order equation, it's simply a quadratic. Also notice that it doesn't say equal to 0 here, so I'm not trying to get the roots, I'm just trying to factor it. So if I use my AC method, I would be looking for numbers that multiply to be 30 and can make a negative 11. Ooh, 5 and 6 could make a negative 11. So I have 10x squared, and I would need a negative 5x and a negative 6x to make a negative 11. Now from the first two terms I can factor out a 5x. This term is negative, so from the next two terms I'm going to factor out a negative 3. Not just a 3, but a negative 3. Negative 6x divided by negative 3 is 2x, and 3 divided by negative 3 is minus 1. So that 2x minus 1 now gets factored out, leaving me with 5x minus 3. One of the things I notice about this problem right away is that there's a subtraction, and I don't like that, so I'm going to change that to addition by adding the opposite. Now I don't have to worry about the subtraction anymore. I also know that when solving a fractional equation, I'm trying to multiply by the least common multiple of each of the denominators to get rid of the denominators. So in this problem, the least common multiple of those denominators would be the x plus 5 and the x minus 5. I need both of those. So here I'm going to multiply this first term by both. Also, with the negative 3 over x minus 5, I'm going to multiply by both. And lastly, with the 2, I'm going to multiply by both. I'm going to squeeze it in there. Okay, so what I have here is both of these canceling. The x minus 5's canceling, the x minus 5's canceling, leaving me with... So I'll be left with 7x minus 9 plus negative 3 times x plus 5 and a 2 times x plus 5. 7x minus 9 minus 3x minus 15 after I distribute the negative, and 2x plus 10. I can clean this up to get 4x minus 24 equals 2x plus 10. Subtract 2x from each side, add 24 to each side, and x will be equal to 17. Remember that we can use our properties of logarithms to combine the sum of two logs into the log of a product. So here the a and the a minus 6 will be multiplied together. When we have a log on both sides, like we do here, the only way that the two sides can be equal is if these arguments are equal. So I'm actually allowed to just cancel these logs. So I'll have the a squared minus 6a equals 10 plus 3a after I cancel those logs. This is quadratic, so I'm going to get all the terms on the same side. I'll subtract 3a, I'll subtract 10. Now I can factor into a minus 10, a plus 1, to get a equals 10, and a is equal to negative 1. Think back to our graph of the log function. It's shaped like that. Notice that there are no values of x for this function which are less than 0, which means the input or the domain of the log function has to be greater than 0. And that creates a problem with this negative 1, because if I put that here for that a value, I would be taking log base 2 of a negative number, and we're not allowed to do that, so I will reject that value, and the answer is 10. I have an exponential equation here. I'm going to change the bases so that they're the same. 4 and 8 can both be rewritten as base 2. 4 would be 2 squared. And 8 would be 2 cubed. Now I'm raising a power to a power here, so we multiply. Again, here we multiply 9x, not 6x. And because the bases are the same, we can set the exponents equal to each other. Subtracting a 4x from each side, 10 is 5x, or x is 2. Question 7, f of g of x. This is called a composition, and what it means is that we're going to take this inner function and we're going to put it into this function wherever we see an x. So we're going to take this g of x function and we're going to take this g of x function and we're going to put it into this function wherever we see an x. So that x right there is a placeholder for whatever we're going to put in for it, and in this case we're putting g of x or 6x minus 1 in for it. So instead of x squared minus 5, we're going to have 6x minus 1 squared minus 5. (36x squared minus 12x minus 4). To find the exact value of sine of 240, I'm going to draw a 240-degree angle. I've got 0, 90, 180, 270. Oh, so 240 is between 180 and 270. So the terminal side of this angle would be here. The initial side is here on the positive x-axis. This is 240 degrees, but that really creates a situation here where this angle is 240 minus the 180. That would leave me 60 degrees. So sine of 240 has something to do with the sine of 60, but we need to find out if it's positive or negative. And in this third quadrant, where this 240-degree angle has its terminal side, there's a t, which stands for tangent being positive, which means everything else is negative, so sine is negative. And you should memorize that the sine of 60 degrees is radical 3 over 2, so the exact value is negative radical 3 over 2.